All right. So today we are going to wrap up our discussion on transforming functions and get into our activity on slope calculations, which slope is probably going to be a lovely breath of fresh air. It's a concept that most students are familiar with and that you may have studied more recently. So I did want to take some time. The way we're going to do our performance task is basically anybody who contributes anything on we're going to kind of do this as a whole group rather than in small breakout groups. And we're going to go in and you're just going to add into OneNote. So if you'll go ahead and open OneNote, we're going to talk a little bit about this. We're going to talk a little bit about the performance task, and then we're going to sort of just work on adding things to this compare and contrast that we have going on. So I've selected two different functions. And what we want to do is discuss lots of things about these functions. If you were to graph them on Desmos, or if you were to just look at, various different parts of them, you can identify the domain and range. We've talked about increasing and decreasing intervals. We have talked about parent functions and graph shapes and transformations. And we've also talked about the zeros of a function and intercepts, like x-intercepts and y-intercepts. And so what I would like to do is sort of work together to compare the two functions that we have, function 1 and function 2. And we want to be able to talk a little bit about things these functions have in common and things that are not common. And when we think about what's common, I mean, okay, yeah, they both have f of x and they both have an x input, but there's more features of that. And so I want to take a minute and I want you guys to kind of read over this. And I've put the parent functions and transformations reference sheets next to it. Of course, if you're looking on your own, you can zoom in and you can actually read these items. All right. This is under, by the way, sorry, this is on OneNote. This is under our collaboration space under performance task 4, and it just has whole class discussion. That's where I'm looking right now. That's where we're going to be adding stuff. So performance task 4, whole class discussion. If you want a copy of the task, you can click on either of these links and it will save it onto your own computer, so you can pull it up and see. And similarly, I sent this handout to you guys yesterday, the parent functions handout. But you could always just like copy and paste it into a document and save it from here if you wanted. So I would like you to go through and add. I'm sorry, I just realized what I did here. Oops. This is supposed to be up here, and this is supposed to be up here. All right, so those are our two functions. And maybe somebody can graph them on Desmos and pop a graph in here. But when you contribute to it, your initials will be in it, and that's how I will grade the performance task. Basically, anybody who participates is going to get full credit on the task. You know what I think I'm going to do? I've changed this. I'm going to make it breakout rooms. But in your breakout rooms, I'm just going to share this. You're still working in the common whole class area, but that way you can feel a little bit more comfortable sharing, because I think that in the whole class, it's like a little extra. All right, so I'm going to make 5 breakout rooms, and I'm going to go ahead and pop you into the room, and you're still going to be working on this same whole class document though, and we'll come back for whole class discussion.
I have a question.
Yes, ma'am.
Is this not a grade? Because I don't see it in the module.
It is, it's going to be for a grade. I didn't think that we would have time to do it, but I recognized after yesterday that we would need a little more practice with this and people needed to get kind of hands-on with it. But I'm going to automatically add in the grade of perfect score for anybody who participates. And I'll excuse people who weren't here, not because like I'm so handy, but because you get a benefit for participating. You're not punished if
Okay.
you weren't here. And that way you can see. Does that make sense?
Yeah. So then, do I need? We just need to put our names on the one that we about to do.
Or just add in anything. You don't even have to put a name. Just literally, if you type anywhere in here, I'll see that you interacted with the document and I'll be able to see what you put in there.
Okay.
Yeah. And so you can go ahead and go to the breakout room and just talk to your folks that are in there. Can I get Rhiannon and Sam and Jalen to join your breakout room, please? Thank you, guys. I didn't mean to leave y'all hanging. So Jenna said, oh, did you see? You did that, huh? Yeah. Sam, are you there? Hey, Raphael. I'm going to add you to a group, and then if you'll go into that breakout room, I'm about to pop in there and follow up with directions so you can catch up with what we're doing.
Okay,
All right.
I cannot be a lot of help today because I'm traveling because of work, so I'm just gonna be listening.
All right. No problem. I understand, and I'll say that when we're coming in. We all have issues sometimes. It's no big deal.
Thank you.
Of course.
Hello?
Hey, Genesis. Did you pop out because you had a question?
No, I messaged, I guess, your co-host profile. I was on my phone. I just walked back home with my dog. So I was on my phone. So I switched it over to my laptop so I could actually be able to interact with the notebook for today.
Oh, I got you. I got you. Do you want me to assign you to a breakout room? I mean, we're going to come back in just a second. Do you know how to get to the document where we are on OneNote?
Yes.
Good. Then you can just hop on. If you're not in a room, it's not the end of the world. We're only going to be in them in a couple more minutes.
Okay. All right.
right.
Thank you.
All right. Bye, bye. And then, or not bye, but I mean, I'm now talking to Furman. Hey, what's up, Furman? Do you need some help, Ben?
How are you doing today?
Hey, I'm pretty good. How are you?
Good. I'm just getting on my phone. My computer's having some kind of problem today.
Oh boy, do I understand. I've had so many layers of issues. And so do you know what we're doing or where we are?
No, ma'am.
All right, so we are looking, I'm going to share my screen.
Okay.
We're in OneNote under performance task 4, whole class discussion. And what we're doing is every breakout group is working on the same document. And all we're doing is comparing and contrasting these two functions that I've provided here. And we're comparing their graphs. We're doing all sorts of stuff like this. And you just want to make some contribution to this document. We're going to come back out in a minute. I just want to make sure that we have identified things like what transformations are happening. How are these these have both of these have increasing and decreasing, or both of these have parts of the function that are decreasing, right? Things like that. So we can really just kind of compare and look at comparing and contrasting, but in particular using those skills that we learned in modules 3 and 4. So like domain, range, intercepts, things like that.
Okay, yes, ma'am.
All right.
All right. Thank you so much.
You want me to add you to a group, or you just want to chill here for a second?
Yeah, let me just chill. I'm going to try to see if I can get my big computer on because I'm looking on a little bitty phone and I can't really see it.
I mean, if you don't type anything anywhere, I'll just excuse you from the actual task. You won't benefit from getting like a little grade boost, but you're not going to be like punished for it or something. Like it's not going to take off any points.
Okay. Yes, ma'am. Thank you.
You're welcome.
I actually have one more question.
Yeah.
Since I'm not in the breakout room anymore, I kind of forgot which one I was in. So which one am I contributing to?
Oh, so you don't even have to worry. There's only one. So it's one for the whole class. That's why I didn't like.
Oh, okay.
I only put you guys in breakout groups because I thought that sometimes it's less intimidating to talk to 3 people than it is to just talk out into the whole world. And so that was just more of like a conversation room than it was like a work room. You know what I mean? Because we're all working on the same document.
All right, I just wanted to make sure because last time
Absolutely,
there was,
yeah,
like,
and
an
I don't want to
issue.
I don't want to mess with you either. All right. Uh-oh. All righty. Hey guys, so I pulled you back over so we could just talk about this a little bit. I'm even gonna add one extra here. I was just like, I'm the one who did the writing on this. I was just thinking, also that both of these, oh no, I was gonna say both of them have an asymptote, but you know what? That's one thing that they're different. All right, so I've just added a few little things on here and let's talk about it. You can obviously see the graphs of these functions. Thank you for my students that went ahead and did that on Desmos. I appreciate it. And you can see, I really, when I'm looking over this, exactly what I was looking for is what you've written. This idea that we have our domain and range represented. We both have a domain that goes up to a domain and range that both go to positive and negative infinity. Of course, in function one, we have an asymptote. So we have to have, and we have both a horizontal and vertical asymptote. So we have items eliminated from the domain. I'm going to add that down at the bottom. In particular, you can see that x cannot equal +3. That's where our vertical asymptote is. And also we can see that there's a range asymptote, or there's a range restriction too. Oops. But y can't be 0. All right, and so I see that we have broken down into some of the differences are things that our horizontal shifts are different. I really like here in this row, on row 3 here, is this idea that next to each other, we have like function 1 is shifted 3 units right. And you can imagine this double-sided arrow saying while the function 2 is shifted 3 units left, right? And so I could even come up here if we wanted to. We could say both graphs have a shift, have a horizontal shift of 3 units, but one is to the left and one is to the right, okay? So mostly what I want you guys to get from this activity and from this section is how we can compare our functions to a parent function to better understand what's going on and how that function has been manipulated, and therefore how the domain and range and other key features have changed. Okay, as you're working on module 4B, please don't hesitate to reach out to me. The next thing that we're going to talk about today, actually, I'm going to stop sharing here and start sharing on my iPad, because the other thing that we're going to talk about today is slope. So I'm hoping that slope is going to be a topic that you guys are a little more familiar with because you've seen it more frequently. Whoops, I don't want to start that video. Here we go. I figure you guys don't need to look at my ceiling. So I'm going to come over here to the notes for 5A. All right. And so slope is a rate of change. In particular, if we're dealing with a line, like a linear function, y equals mx plus b, slope is kind of like that multiplier A that controls your vertical stretch or compression, okay? It tells us how steep or gradual the slant of a line is going to be. And we calculate that by making a ratio of, if I move from one point to another point on a line, I have a ratio of the vertical distance I move over the horizontal distance that I move. Some people think of that as rise over run. Some people think of it as change in y over change in x. This symbol delta, this Greek alphabet letter, is a Greek alphabet letter, delta, but it means change. And so when I see this, I would pronounce that change in y over change in x. All right, and it's the same thing as the slope. So to calculate that change, I can find the difference between the y values. That's going to be the same as this change in y. And I divide it by the difference in my x values, which is the same as my change in x. So I'm going to show you a couple different ways, or like I'll show where some problems are easier to use the slope formula. For example, if you're given like a written problem and there's just a couple of points in the problem and you're not provided a graph, then the slope formula is very handy. If you have a graph, I think that drawing a triangle to connect those two grid points is actually significantly easier than trying to use the slope formula. So I'll show you both. So I have this on here, that the average rate of change is a type of slope. Average rate of change is the slope between 2 points on any graph. So it doesn't matter what the shape of the graph is. If I take this point and this point, we'll call this x equals A and x equals B. That makes the output, this is f of A, and this value is f of B, the output when x is A. Then what I do is I can make a line connecting those, and the average rate of change is the slope of that line. So you're also going to see slope related to average rate of change. If you have a line, if your graph is a line, the average rate of change is the slope. If your graph is not a line, the average rate of change is the slope between those 2 points, which is different for every 2 sets of points. However, a line is defined to be points that all have the same slope. And so that is just the other thing, is it's still a change in y over a change in x. And it's still the same ratio. It's just that it doesn't have to be on a line when we think of this method. So say, for example, I wanted to find the slope between the points 6, -6 and -2, -28/5. My slope formula is change in y over change in x, which is the same as y2 minus y1 over x2 minus x1. You want to be careful to label your points because it is real easy to get mixed up. It doesn't matter which point is x1, y1 and which point is x2, y2, but it does matter that you have that they're both like the same one, is the same points from the coordinates from the same point are in the same position in your ratio. So that if I start with my change in y and I'm going to do like this if I want to find my change in y by subtracting these two, I started with this number in my y's. So in my change in x, I have to start with this 6 as well. Does that make sense? Because I just want to make sure that whether it's x1 or y1 or x2 or y2, the points from the same one are starting the subtraction. According to how I did that subtraction, this is how it would be labeled. And just FYI. So I'm trying to open everything up so I can make sure if I have. All right. So I am just monitoring the chat for questions. And I'm also more than happy to take questions if you unmute yourself and just interrupt me. If I'm looking down, I can't see you. So, all right. So to calculate this slope, what I'm going to do is I'm going to take these changes in y over change in x. My change in y, I said, was -6 minus -28/5 over 6 minus -2. Subtracting a negative is the same as adding a positive. So this is the same as -6 plus 28/5 over 6 plus 2. On the bottom, that's easy. That's 8. But on the top, I need to find a common denominator. So this is -30 over 5. -30 over 5 plus 28 over 5 is -2 over 5. Last but not least, -2 over 5 divided by 8 is the same as -2 over 5 times 1/8, which gives us -2 over 40, or like in simplest form, -1/20. Are there questions on this example? All right. If instead of starting with points in a problem, you're starting with a graph, I think that drawing a triangle between points is actually the easiest. Remember that all lines have equal slope between their points. That means that I can select any 2 points on this graph, but in particular, I should strive to choose only points that are on perfect whole number grid coordinates, both because you can see up here that it sucks when there's fractions, but beyond the fact that it's uncomfortable to have fractions, it's also it's hard to eyeball it accurately, and so you might wind up getting not the correct slope. So we can pick any 2 points. I'll pick these 2 because I like the look of them. And I'm going to draw a slope triangle between them, which is just the right triangle, like if I was going to do the distance formula. I'm not calculating the length of the segment between them because that would be distance. Instead, what I'm doing is forming the ratio of increase in y over increase in x. My change in y, well, y went from -7 to +3. That means starting here, I would have to go, I would have to go up 10 units because I go up 7 to get to 0 and up 3 more to get to 3. So up a total of 10. And my change in x is +2. You want to make sure that you're assigning the correct signs to these. If I start at this point here, I'm going in the positive direction and the positive direction. So my slope is going to be positive. If I had instead started at this upper point, I could have gone down -10 and left -2, in which case my slope would be -10 over -2, which is still +5. So it doesn't matter which direction you're going. It just matters that you have you've accurately calculated the distance, not the horizontal distance and the vertical distance. If I had picked a different point, like if I had gone through 2 different points, like these two, I'll still get the slope of 5. My change in x is +1. My change in y is +5. 1, 2, 3, 4, 5. So my slope is 5/1, just 5. Okay. And all of these, this number of the slope is 5. Any 2 points are going to give me that same slope. If I had done the top and bottom points, I would have gone over 3 and up 15. 15 divided by 3 is 5 again. Right. Oh my gosh, this is my friend Marissa. She knows I'm in class, so I don't know why she's getting so texty. Maybe it's an emergency. I don't know. Should I look at it? Oh my God. It was not an emergency. Okay. Sometimes, just when you think an idea is pretty straightforward, there's going to be something that gums up the works. Horizontal and vertical lines are a little weird, okay? Remember that our slope is our change in y over our change in x. Here, we have no change in y. As I start from one point and I go over to the other one, I increase my change in x from the 2 labeled points is over 5. But my change in y is 0. So my slope is 0/5, which is just 0. All horizontal lines have a slope of 0. But what do you think would happen if I had a vertical line?
Infinity.
Almost the opposite of infinity.
Oh,
I know that that's vague. I'll get there. Don't worry. If I had a vertical line, say x equals 2, and I wanted to calculate the slope of that line, we could say that this is 2, 2, and let's say this is 2, -1. I know that I can pick any whole numbers that I want because the input is always going to be 2, and the output changes, but the input stays the same. So no matter what x I choose, or no matter what y I go to, x is always the same. So on this one, my change in y is +3. But my change in x is 0. So my slope becomes change in y over change in x, which is 3/0. If you're asked to find the slope of a vertical line, it's called an undefined slope and it does not exist. So you would type in D and E. Okay, so that's why. And if you get confused about which one is a zero slope and which one's undefined, just remember it's the change in X that can't be zero. So if X never changes, it stays on the same X line, then it's an undefined slope because we would be dividing by zero. Alrighty. The other thing that you're going to be asked to do is you're going to want to be able to graph a line. And to graph a line, there's two main features of a line that we consider. The slope, which we just talked about, how tilty it is. That's how we move from one point to another on the line. But the other thing is like a starting point, like which point do I start at? And our universal starting point is the y-intercept, mainly because that's when X equals 0. So it's like our original case, you know? So the y-intercept is the letter B, like we use that to represent it. In statistics, it's just AX plus B. They don't use M for slope. And in fact, in mathematics, we don't use M either. We use the Greek alphabet letter mu, but apparently students really get uncomfortable when you say mu instead of M. And so I guess the entire country of America decided that we were just going to disregard that mu, which looks like this, is the symbol for slope. But internationally, that's what they use. And in calculus and beyond, that's what they use. So well, it looks like an M. All right. So if you want to graph a line using slope and intercept, you're going to be given some sort of information. Maybe you'll be given a word problem. Maybe you'll be told what the slope is or what a point is on the line. But you're going to have to use the information from a problem to find the slope. And you may have to solve for the y-intercept, or you may be given the y-intercept. If you are given a point other than the y-intercept, you're going to have to solve for it. If you're given the y-intercept, oh, yay, winner, winner, chicken dinner, you can just write your equation. All right, so this shows doing a little system of equations to solve for b, but I'll show you what it looks like if you actually have to solve for b. It's not that hard. So if I want to graph the equation 4x minus 3y equals 12, you could just come up with the intercepts, let x equal 0, then let y equal 0, and see what the other points are, graph those two intercepts, and draw a line through them. But this section is all about graphing using slope-intercept form, so that's how I'm going to show it. The first thing you want to do is get this equation into the form y equals mx plus b. To do that, I'm just going to solve this little equation. I have 4x minus 3y equals 12. I want to move this 4x away from my 3y because I would like it to be y equals ultimately. This gives me negative 3y is equal to negative 4x plus 12. 4x and 12 aren't like terms. I can't combine them. I could have written 12 minus 4x and it still would have been correct. However, since I have the function y equals mx plus b, I'm going to put the thing that has x with it first. It doesn't really matter. Just make sure that the minus sign goes with the 4. All right. Last but not least, I divide every term by 3, negative 3. And that means every single term. If I had just divided by 3 a single time on the right side of the equal sign, I would have to use a line that went across the entire fraction, or I would have to make a fraction bar under the entire right side of the equal sign. And then I would have to distribute my division, which still means every single term is going to get a divide by 3. So it's easier to just go ahead and take every single term and divide it by 3. Negative 3. When I simplify it, I have slope-intercept form. Y is equal to 4/3 x minus 4. That tells me start at y equals negative 4. Go over 3, go up 4. Up because it's positive. I would say go right 3, but the other thing that people get wrong is they use the wrong one for your change in X. And when I see 4 over 3, that fraction 4 over 3 tells me in the fraction to go over 3. So I'm like, cool, I'm going to do it. That's how I remember it. That's just a mnemonic device. You can thank me later. All right, so I start at y equals -4 and I put a dot. Now I'm going to go over 3. 1, 2, 3 in the positive direction because I have a positive slope. And then I'm going to go up 4. 1, 2, 3, 4. And I make a dot. Now, I could just draw a line through those, but the farther I get away from those points, like the harder it's going to be to make sure my line stays accurate in the corners. So I'm just going to go over 3, up 4 a few more times. Over 1, 2, 3, up 1, 2, 3, 4. Here's another point. Over 1, 2, 3, up 4. Here's another point. So I can just do that. I can go left 3 and down 4. I'm just doing that so that when I draw my line, you want it to fill the entire graph space. And when I try to do this by hand, I tend to drift from the true line unless I have a few more points on there. But you only need 2. Okay. Okay, fine. Change in y was equal to +4. Change in x was equal to +3. And so that's how we can graph using slope-intercept form. Just get it into y equals mx plus b. Maybe it's already like that when you start. Huzzah. Okay. Are there questions on how to do that? I'll take a little bite of my lunch, my fancy lunch. That is the exact same problem. Oops, I don't know what I did. Here's a different one. I think you'll notice right away, there's no x in this equation. That's all right. It's going to be a horizontal line. I'm going to put it in y form, meaning I'm going to solve for y. And this gives me the equation y equals -4. This is kind of like y equals 0 times x minus 4. So I go down to y equals -4 and I make a dot. And then there is no change. Does that make sense? Like it never changes from 4. It stays at -4. It just stays being negative. The line y equals -4 is the line that goes through y equals -4 on the graph. That's it. If I had x equals some number, I would go over to x equals that number and put a dot on it, and then draw the vertical line that went through that x value. So y equals -4 is the line where the output is always -4 no matter what x is. All right. So here's a fun problem. The reason I've included this problem is because it does a couple of interesting things. One of them is that we're going to talk about the practical domain, which means that just because, like when you're using an equation to model a real world scenario, you have 2 things going on. You have the equation and what that looks like on a graph and how that behaves. And then you have the real world scenario that equation is representing. And that real world scenario, maybe not all of the points that you have on that line are going to be important. Maybe they can't all be interpreted the same way. So you want to decide like, where is this information valid? And that's what we call the practical domain. So this problem says when a diver descends in a lake or ocean, pressure is produced by the weight of the water on the diver. As a diver swims deeper into the water, the pressure on the diver's body increases at a rate. We use the word, whenever you see the word rate, you know it's a slope of 1 atmosphere of pressure per 10 meters of depth. That's our slope information. Since pressure is y equals pressure, x equals depth. Then our change in y over change in x is our change in pressure, 1 atmosphere of pressure, over the change in depth, 10 meters of depth. Okay, so whenever you see the word rate or per or for every, that's probably going to be your slope or your rate of change information. As we continue to read, we see that we also have that this is a graph of that relationship. So all we need to do is identify the x-intercept, y-intercept, and slope. Slope is great. We already did that just for fun. I just wrote down 1/10 and I looked back at here, and you want to be careful because when we think about going deep in the water, we think about going downwards, right? But our y isn't our position in the water. Our y is how much pressure is happening. So the deeper you go, the stronger the pressure is because there's more water on top of you pushing down. That means that our graph is increasing. So our slope is positive, even though you're getting deeper in water, which feels like you're going negatively. It's a positive slope because the pressure is what's increasing, and that's what we're measuring with our output. The x-intercept, let's skip that for a second. The y-intercept is the pressure when the depth is 0. All right, so the y-intercept is right here. That tells us our B is 1. Remember, your intercept is given as a point x comma y. The x-intercept is where this graph crosses the x-axis. There's a couple ways you can see it. Do you see right now that this line that we're shown does not cross the x-axis? All right. Can you imagine if we extrapolated? This is like looking here, and I went over at 10. Our pressure is here at 2. That if I wanted to, I could back up like this and see where it crosses, that eventually it's going to cross that x-axis. And the way that we can figure that out, since we can't see it, is one of two things. We can either back up using the table. Like if this is if I'm increasing in 1/10 or plus 0.1 here, and I go up plus 0.1, I can imagine going backwards, which would be -1, 0.9, right? -2, 0.8. Like I can go all the way back until I get to the value that y is, to the value that x is when y is 0. Or I can back up using slope. Notice my slope means I go over to the right 10. To go up 1 unit. Since the slope between any 2 points is the same, sorry, you'll see why I had to do that in just a second. Because it doesn't quite work. Going over plus 10 and up 1 is the same as going left 10 and down 1, which will take me back to that x-axis. So the x-intercept is at negative 10 comma 0. There's even one more way to find it, y'all. The equation of this line, y equals mx plus b, is y equals m is the slope, which is 1/10, times x plus b. So since m equals 1/10 and b equals 1, we get this equation. And I could substitute y equals 0 to find what x is when y is 0, which is the x-intercept. So 0 equals 1/10 x plus 1. I'm going to subtract 1 from both sides, giving me negative 1 equals 1/10 x. And then I'm going to multiply both sides by 10 to cancel out that denominator. Giving me negative 10 equals x. So that tells us again my x coordinate of my x-intercept. But the reason that this is included on here but what does negative 10 feet of depth mean? So when x is negative 10, the pressure is 0. But what is negative 10 on x? Like, what does that mean in the context of this problem?
Upside 10.
Yeah, it's like, since we're going underwater as x increases, when x decreases, I'm going above water. And the reason normally that would be fine. Okay, fine. I'd be like, oh, when you're 10 feet above sea level, the pressure is 0. But that's false because air pressure and water pressure are different. And there is no such thing as a place. Like, if we can say one thing about the earth, it's that we all feel pressure at all times, no matter where we are. And even though air pressure exists, it's different than water pressure. And if air was as heavy as water, oh, we would be dramatically different as evolutionary species. We'd be much shorter and probably have very robust little bones. We'd walk around like little stocky people. Long story short, it's outside. So in the context of the situation, my y-intercept is 1. That means that I have 1 atmosphere of pressure when when I'm at sea level. That's interpreting it in the context of the problem. When my x-intercept is the depth at which I feel no pressure, that would be, according to this line, it would be at 10 feet above sea level. However, there is no interpretation of the x-intercept in the context of this problem because it's outside of the practical domain. Water pressure doesn't apply in the air. All right. And then last but not least, the slope is how quickly the pressure is changing. So when I specifically interpret my slope, I'm going to say the pressure exerted on a diver increases by 1 atmosphere for every 10 feet of depth underwater. This part, that's my y variable in context. This is my change in y with units. For every needs to be included, but 10 feet is my x with units. Change in x with units. Of depth underwater, that's my x variable in context. It's maybe one of the most important things you're going to learn in this particular module is how to express slope. All right. I know we're about to go. I'll be done in 1 minute. Don't worry. The y-intercept was just my pressure when the depth is 0. So it's y when x is 0. And the x-intercept, that has no interpretation within the context, no meaning. In the context of this problem. But it's normally x when y equals 0. All right. So I am now, I'm going to stop the recording. That reaches the end of our class session for today. Thank you for staying, and you're welcome to stay along if you have any questions.